All right, so now we're going to take a look at one important application of this. We're going to see another important application in the next video. But for right now, we're going to end up looking at what ends up happening whenever I end up taking a coil. So what we've been dealing with so far were things where we had one loop, right? So we have one path to go around. So what we want to think about now is what happens if I've got more than one. So if I've got a coil, right? So if I have a coil, then if I end up thinking about turning it on its side, a coil is going to consist of a bunch of little circles that are back to back, right? So if I end up having that where I've got them back to back, notice if we end up turning it back on its side, the way that it's going to end up giving me an EMF on the first one, whatever the polarity might be, if the magnetic field is the same throughout, it will match your magnetic flux through the next one, through the next one, through the next one, through the next one. And so the total EMF, if you have a constant magnitude magnetic field, is going to end up having the same value of magnetic flux through each one of these. So again, a constant flux is not going to do anything. Constant flux doesn't produce an EMF. It basically, for the most part, is as if it wasn't there. But what we want to think about is what happens if I end up changing it in a way that turns out to be useful. The way I'm going to think about changing it, I'm going to end up imagining now I have a permanent magnet and in a horseshoe type. And in a horseshoe magnet, we've not really talked very much about these. The details are not beyond the scope of the course, but I don't think they're sufficiently useful for us to end up worrying at a lot of length. For our purposes, we will pretend like you have straight field lines from the one to the other. It's not perfectly true, but it turns out, even though it's not perfectly true, that you end up having an overall change of a factor having to do with the asymmetry of it, and that can end up being a multiplicative factor. So if you say we ended up changing the magnetic field a little bit, we can end up getting to this exact thing. So the ultimate form doesn't depend on the fact that this has to be perfectly uniform, even though the way we're going to calculate it will assume that it is. All right, so in this scenario, let's say we end up having this horseshoe magnet. So I'm getting a constant magnetic field from one end of this to the other. And I'm going to end up taking my horseshoe magnet and spinning it around. And I'll spin it in such a way that it moves at a constant angular velocity. Remember from last semester. Okay, so when we have that, the reason why I need to talk about the coil as being a little different is that to find my total EMF, I have to add up the fluxes from each one. So the total is going to be the number of turns multiplied by the EMF that you get for a single turn. So if I do that, I have the diagram that I showed there, which I know is hard to read, so hopefully the video will help you see it a little bit. So in this situation, my EMF for one of them will be the minus the first derivative of the flux, and my magnetic field, the magnitude staying the same, the area is staying the same, but the angle between the magnetic field and the area vector, which of course is pointing straight up, the angle between those is changing. And so the dot product, so the magnetic field magnitude stays the same, so that makes it easier. The area magnitude stays the same. So magnetic field being the same magnitude, it factors out of the flux, and the integral of your differential area is the area. And so then the magnetic field dotted with the area will end up being the product of the magnitude of the magnetic field times the magnitude of the area times the cosine of the angle between. Dot product from last semester, right? then we multiply that by the number of turns, because you get one of those for each of the little turns. So then your total will end up being minus n times the first derivative of your magnetic field magnitude times the area magnitude times the cosine of the angle between. If we have an object that's rotating at constant angular velocity, we mentioned last semester that the angle will be equal to your angular velocity times time plus a constant, because it depends on where you started, when you started your watch, right? So we end up putting that in as theta 0. So, and it turns out that for our purposes, what theta 0 is really doesn't matter a whole lot at all. And we'll end up seeing later why that is more important. So when I end up then computing my EMF, it will end up, the number of turns isn't changing. I'm not changing the shape, so I'm not changing the area. It's the same permanent magnet, so I'm not changing the magnetic field magnitude. The only thing that I take a derivative of then is the cosine of the angle. So the derivative of cosine is minus the sine, so the minus sign in front cancels with the minus sign from the derivative. So I end up ultimately with my number of turns times the magnetic field times the area times your angular velocity times the sine of your angular velocity times time plus theta 0. So what's going to happen with my EMF in this situation is going to be something that's kind of strange compared with everything else we've done so far. Because sine, of course, oscillates between +1 and -1. So it will end up bobbing up and down and up and down and up and down in time with your angular velocity. Remember, your angular velocity was in radians per second because we want to take the derivative. Otherwise, we have this other factor floating around if we wanted to use some other angle unit. So when you have an EMF that oscillates in time like that, you end up having what's called an alternating current. And alternating current is an EMF that ends up oscillating in time such that it bobs up and down, positive to negative. So one of the reasons why whenever we talked about a AC generator back when, where I just told you what drawing would look like, we had the little wiggle inside of a circle with lines coming out from both sides. What that's about, the reason why we don't draw like a battery, you have one line that's long, one line that's short, right? The reason why you don't draw it that way is that which side is positive and which side is negative is constantly flipping back and forth. The other thing you might end up initially saying is, well, in that situation, the average is going to be 0, right? So it may not be obvious that this has any value, but we will end up seeing, not in the next set of lectures, but the ones just after that, we're going to end up seeing then why that actually can be very useful. And the last thing we'll end up saying is that collection of constants at the beginning, the number of turns times the magnetic field magnitude times the area times your angular velocity. So that has units of volts, because EMF, of course, has units of volts. And the angle, always angles are dimensionless, so the sine of whatever is dimensionless value. So that quantity we end up labeling as V subscript 0. That's just a standard way of saying it. And again, it has units of volts. And that gets us really, really close, but not quite there, to what I said way, way back when. I said we were going to introduce the concept of voltage. Voltage is very close to what this V0 thing is. So notice it's not a constant potential difference. V0 is the maximum amount of potential difference you can get from one side or the other to this. But notice the maximum is not this side's always plus, that side's always minus. That those flip back and forth in time. So again, your average is 0. It is exactly 0. And something that averages out to 0, you might initially think is not going to have any really lasting effect. It does, however, turn out that the reason why most everybody is going to be able to see this video is specifically because that's not true. It ends up having an important effect, and we're going to see a lot more about that in subsequent work. Right?